After setting up the ID and selecting our target development board, we are now ready to start our journey with ARM Cortex-M microcontrollers. So let's start! For our very first application, we will create project the simplest way possible. For now, we don't want to introduce too much advanced stuff that is not really needed when starting with Cortex-M microcontrollers. The plan is to increase difficulty level over time, and right now we want to get to the point where our application can control basic peripherals. Somehow, we will follow the KISS principle. We are just starting, so everything we do today we'll do as simple as possible. There will be time for advanced topics later. We will skip implementing everything that is happening between microcontroller reset and main function call. But don't worry, we will cover this part of application in later videos. It's just not essential right now. Also, by saying the simplest way possible, I mean using some code generation. I don't really like using any code generators in production code, but I think they are helpful when it comes to collecting all basic elements needed to build the application and reduce time to start development. In my Visual Studio Code, I have an empty main.c file. We need to add a definition of a main function with infinite loop. Additionally, we need a variable that is incremented with every loop execution to easily visualize that our application is indeed running. Now let's try to compile and see what happens. So the compiler built our application, but not without warnings. It complains about undefined reference to _exit function. Basically, it means we are missing a definition of this function, but according to reference on c++.com website, this function terminates the process normally by returning control to the host environment, so we don't need this function because we are creating a freestanding application without any host operating system. How do we get rid of this warning? We must let the compiler know this is a freestanding application. Great, compilation has finished without any warnings. Now, let's switch to Ozone and load the binary to our board. For target device, we select STM32 F411CE, and for register set, we select Cortex-M4 with FPU. On the next page, we pick SWD as target interface and leave the rest as it is. Next, we choose our binary to debug and click Finish. Ozone will now set up the project for us. When it's done, we can try to download our binary to the board. At this moment, we should start debugging our application, but unfortunately it's not possible as the microcontroller is immediately going into hard fault exception state. The reason for this is faulty binary file that is not built with comply to memory structure inside the microcontroller. To fix that, we need a linker script that will tell the linker what are the memory areas and output sections. Inside such linker script file, we can see this information. For example, here we can see defined flash and RAM memory areas with their origin addresses and lengths. More details about linker scripts and how to write them we will cover in future videos. Also, how to obtain such a script I will explain in a moment. Now that we have our linker script, let's add it to our building process. Now we again get another warning during building process. This time it's a warning about the missing entry symbol reset handler. But wait, what is reset handler? Why is the compiler complaining about something we are not using in our code? Well, actually it's our fault that linker warns us about this. By passing the linker script file in build command, we also passed a command setting reset handler as an entry point in our application. What is more, this is the part of the code I said we will skip at the beginning. It is the code responsible for what's happening after a microcontroller reset and before main function call. Okay, so what do we do if we want to skip implementing entry point code? We simply generate it. For beginners with ARM chips, this is the easiest way to get application running and not care about microcontroller reset handling and its initialization. For our Blackwell board with STM32 chip, we will of course use a code generator provided by ST, and that is STM32CubeMX. Link to that in the description down below. In CubeMX, we want to generate a project for our MCU. As a part number, type in STM32F411CE, and according to official board repository on GitHub, last two symbols are US6. After selecting microcontroller, Cube loads empty default configuration for this chip. We leave pinout configuration with no changes, and in clock configuration, we set main CPU clock HCLK to 100 MHz. Cube will warn us it needs to change clock source to properly set up our clock frequency. Again from GitHub repository, we know that external high-speed crystal is 25 MHz, and this matches the configuration in Cube. In Project Manager, we type in project name and pick its location. And now the most important part of the configuration here. In toolchain/id, we pick makefile. Additionally, in advanced settings, we want to change libraries to LL, which stands for low layer. Configuration like this will provide us few things. First, initialization code will set up our MCU to run with maximal clock frequency, which is 100 MHz for this chip. Second, we will get set of libraries that we can immediately use to work with peripherals. And finally, generated makefile will automate build process and spare us typing long make commands. When everything is set up, we can press generate code button. And this is where code generators from microcontroller vendors are useful. As beginners, we quickly get startup code and painless start of the project. For now, we are not interested in this code. We just want to run our application as soon as possible. We already have linker script file, which, by the way, I generated earlier, exactly the same way using CubeMX. If we look carefully, we can notice we also got a makefile. This is exactly what we wanted by choosing makefile as a toolchain in project configuration. Inside this file, we can see a bunch of variables collecting all the files needed to build basic application, together with compiler and linker flags. Believe me, knowing all this and setting it up from scratch is difficult and requires knowledge and experience to do this properly. Right now we are beginners and we will use this makefile as it is to build our application. To compile, we have to let make know where is our compiler located on our hardware. To do this, when typing in make, we additionally have to type gcc_path equals path to our compiler bin folder. Let's build our code and finally get a valid binary file. Now we can create awesome project and use new binary file to flash our microcontroller. The only minor issue now are source files not found within Ozone project. This is caused by the fact that we have built our application using a Linux subsystem, and elf file contains source files paths coming from there. Fortunately, Ozone has the possibility to replace these paths with our own. To do this, in console type in project.add_path_substitute, open parentheses, quote /mount/d, quote, comma, quote, d:/quote and close parentheses. Now we are able to see our source files. Let's flash the board and run the application in debug mode. Alright, but we can't really see if anything is running. That's why at the beginning we added an infinite loop with variable incrementing. We just have to copy it over to main function also generated by CubeMX. Now when we rebuild and rerun our application, we can add our variable to watch the data, and after setting refresh rate, we can see its value is changing. Perfect! Now that you know how to create your first application, I encourage you to try on your own. If you have any questions, ask me in the comments section and I will do my best to help you. Also, in the description under the video, you can find a link to GitHub repository containing application source code. So, let me know what you think about this video and until next time.